Can everyone see that? Okay.
Blackboards are not a strong part of this.
Really? I thought they're awesome. Yeah. Yeah, that's the best Blackboard I've used like ever. Yeah. Right. It's important to challenge students to strain their imagination even more. Physics is too easy. Got to throw some random Blackboard obstacles in their path.
Okay, well, we're lucky. There were no delays at Ben Gurion this morning. Nima flew in at 6 a.m., but we're always happy to see him here. I think he's lectured every school that I directed, just about.
It's impossible to say no to you, David. and Eliezer.
But, so we're delighted that he's able to stand up straight, and he's going to give 4 lectures. Wow. The first 3 are on something called scattering amplitudes in the positive Grassmannian, but the real title is how you get space-time from the permutation group, right?
That's the title.
And the final lecture will be on what we can learn from the recent discovery of the Higgs, right? So, great pleasure. Nima, I hope you can survive through the talk.
Oh,
and then you have to give another talk today and 2 talks tomorrow?
It's all good. It's all good. It's all fine.
No problem.
Thursday. So it's absolutely wonderful to be back here. As always, this is one of my favorite schools out to lecture. Normally because the Blackboard quality rocks. But, well, it's okay. As David said, I'll be giving 3 lectures plus hopefully minimal spillover into the 4th lecture. We'll see how it goes on subject related to the physics of scattering amplitudes and gauge theories, of which I understand you've already had some wonderful lectures by Zvi. I guess more to come on some of the on certain aspects of the problem. What I'll be talking about will take off from some of what he said, but will be, I think, largely complementary. And the last lecture on at least some thoughts about what the picture of the world might look like consistent with 125 GeV Higgs. Just a few minutes of general motivation for thinking about this subject. I'll try to keep it short. This motivational part tends, when I normally do it, tends to go on a long way. So I'm going to give myself like 5-10 minutes max. Okay. You know, probably the biggest real intellectual challenge in our business in this century, if you go to any of David's talks on the future of fundamental physics, there's a slide in there that emphasizes the need to understand the emergence of space-time. We know that space-time has got to be is an approximate notion because of gravity. We know that gravity makes it impossible for there to be local observables, not just that space-time breaks down to the Planck length, but more importantly, that there's no such thing as local observables at all when gravity is included. The only sensible observables we can even talk about, quantum mechanical observables in the theory of gravity, live on the boundary. And we beautifully know, at least, how to make sense of that in situations where we have a nice boundary like ADS, where the time on the boundary is the same as the time in the bulk. So we have dual descriptions of the same physics, but where the 2 dual descriptions are both ordinary normal physical systems with a time and a Hilbert space and a Hamiltonian, and they evolve and everything is fine. But we know that our own universe doesn't look like that. Our own universe is cosmological, it's expanding, it's accelerating. And probably the very hardest conceptual problem that we have to deal with is to figure out what to even talk about in a universe that looks like that. We don't, of course, we still don't have local observables, but even worse, we don't even seem to have any decent quantum mechanical observables to speak of at all. In an accelerating universe, we have what we see now out there in the universe is everything we're ever going to get. We have finitely many degrees of freedom. We can't talk about any precise quantum mechanical observables because precise observables require us to separate an infinitely large apparatus from the system that we're studying, and we can't do that when all the degrees of freedom, everything is finite. So that's probably the very hardest problem that we have to deal with. And it's clear that at least one very important new thing that we have got to learn to talk about is whatever the heck emergent time is supposed to mean. That's, after all, being the central difference between our own universe, which is cosmological, and the toy tin can of anti-de Sitter space, where we know how to make sense of everything. So the question is how to make sense of emergent time, emergent space-time in general, but where time is important. Something else I want to add to the mix while we're waxing philosophical for another 3 minutes is that it's also conceivable that we need to think about some kind of deformation of quantum mechanics. I'm not talking about something stupid. This is a sort of a heretical thing to say because many times before in the history of our subject, people have talked about whether quantum mechanics needed to be modified, and every time they've been wrong. But every time before, they've been wrong in a situation where there was something quantum mechanical that you could in principle talk about. So for example, in the problem of black hole formation and evaporation, where famously people questioned quantum mechanics, there quantum mechanics wasn't begging for mercy and telling you that, that there's no way you can even ask a sensible quantum mechanical question. There was a sensible quantum mechanical object, the S matrix, for producing the black hole and having it evaporate. It's just that people thought that that gave the wrong answer. Okay? But there was no inherent kinematical problem. I mean, quantum mechanics wasn't kinematically screaming for mercy. The difficulties we have cosmologically, and only cosmologically, is that quantum mechanics seems to be begging for mercy. We don't seem to know how to define precise quantum observables. Maybe we'll find some clever way of defining them, but that's certainly the part and parcel of the difficulty that we have. It's really quantum mechanics and gravity together that make it impossible to define local observables. And in the most extreme situation of how to make sense of our very confusing accelerating universe, perhaps both things need to be thought of in a different way. Now, one can say all you want, even let's just talk about emergent time or emergent space-time, which is a much more generally agreed upon thing. You can say all you want that that's an important problem and you should work on it, but it's very hard to get up in the morning and go sit at your desk and say, today I will understand emergent time. I will work on emergent time. You have to do something. You know, you can't just stare at the piece of paper forever. The question is, what can we do? I mean, how can you actually attack this problem in some kind of accessible way? And as usual, there are sort of frontal attacks that you could try, but there might be sideways ways around to getting to the same kind of issues, which are more sturdy and robust and reliable. And I just want to give a quick parable because it's played a very important role, at least motivationally for me, in thinking about the subject that I'm going to be talking about, which is, of course, which is just going back to a previous era where there was a similarly sort of seismic shift that had to happen. And that was the seismic shift in going from classical to quantum. There, of course, we had to give up determinism. And imagine that you're a classical physicist in the year 1780, okay? You're visited in the middle of the night by the ghost of theorist future, okay? Who wakes you up in the middle of the night and says, in 1930, I have a hint from the future, in 1930, determinism is gone. They vanish into the night, as ghosts of theorist future are wont to do, okay? So you're very excited, right? You have to do something with this information. You certainly have to write a paper before the Ghost of Theorist Future gets to the next guy. So what do you do? What do you do with this incredible hint from the future? Well, there's two things you could do. The idiot thing and a more sensible thing. The idiot thing to do is to say, I know, somehow determinism is wrong, so I'm going to guess the correct theory, and I'm going to guess the correct theory, and the guess is that I'm going to add stochastic terms in Newton's laws. Okay? You can do that if you want, but it's clearly a stupid thing to do. It's false, and it's nowhere near what needs to be done to actually guess the correct theory, which is quantum mechanics. You've got to invent all this tremendous different kinematic starting point and everything, right? So it's hopeless, it seems to me, hopeless to just guess the right answer. And attempts at doing so in some half-assed way are likely to just waste your time and everyone else's time. There is something else that you could do, though, which is to say, okay, this is a very deep hint from the future, but it's telling us that determinism isn't really there. That means that its presence in the theory that we have right now is somehow a mirage. It's not really fundamentally there. There's some other theory with its own rules, its own principles, its own ideas. And in some correspondence principle limit, in some limit, it reduces to the theory that we know and love. But since that's true, there must be some way of talking about even the physics we know and love now, classical physics, to this person, in such a way that determinism isn't manifest. After all, it isn't really there. If it isn't really there, there must be some way of talking about all of physics, in particular the physics of classical physics, in a way that doesn't make determinism manifest. Now, this is a strategy you can sink your teeth into, or at least think that you can sink your teeth into, because you can go about trying to reformulate classical physics in a way that doesn't make determinism manifest. Why would you do such a crazy thing? It's a clockwork universe handed to you by Newton, right? You would do this because of this hint from the Ghost of Theorist Future, who says it isn't really there. So you say, God, it seems crazy, but there's got to be some way of reformulating classical physics where there's no determinism. Is there such a way of reformulating classical physics? Of course there is. It's a principle of least action. When you first hear about the principle of least action, it's very surprising. The particle goes from A to B, seems like it's sniffing out all the paths and picking out the one that minimizes the action. It doesn't sound very deterministic. You don't put in the words determinism. It's not obvious that the results are deterministic. Of course, it turns out by the rules of how you do the variations and the kind of paths you allow, and et cetera, it's equivalent to Newton's laws. It's not new physics, but it's a radically different starting point for formulating the physics. And of course, the reason that new formulation exists is quantum mechanics. It is because the world isn't deterministic, and the h-bar goes to zero limit of quantum mechanics doesn't land you on Newton's laws, but it lands you on the principle of least action. Okay? So this is always a strategy that you can have. When you think that there's some core principles in the physics you have now that you have to abandon in the future, you can either try to randomly guess the answer, or you can do something more conservative but more robust, and where you cannot, the odds of fucking up are lower. Okay? You can try to reformulate the physics you have in such a way that doesn't make heavy use of that concepts that you're trying to get rid of. Okay? All right, so now, yes?
Just a historical insert.
Yes.
The Ghost of the Future did appear.
Right, yeah.
It was called radioactivity.
yes, right.
And nobody had the biggest idea how to utilize that.
Well, actually, so let me we can have a wonderful dinner time discussion about this, because actually people say that no one would have invented quantum mechanics if it wasn't for experiment. And I think this is false. It may have taken 50 or 100 years longer, but people would have done it, and they would have invented the principle of least action eventually. And there's a nice history story I could tell you about this. Hamilton was doing this already, by the way. Hamilton already had formulas with e to the I action in them, and was thinking about summing over paths. And one of the reasons he was doing this is people were trying to understand the principle of least time for light. Okay, and that is, I mean, making that equivalent with wave mechanics is the path integral, right? So people were, it would have taken a lot longer, and I think even if they had found the path integral, it would have taken them a lot longer to interpret it as a unitary object and so on and so forth. But I think, even this parable, something like it could well have happened if it wasn't for radioactivity and other things intervening and giving it a jump start. Anyway, so that's just to say that we're in a very similar situation today. It's locality, definitely, and perhaps even unitarity that might be on the chopping block. And again, I stress unitarity only in these very fancy cosmological situations, not in any ordinary situation. But we have a way of proceeding which is where we can be sure whether we're on the right track or not, which is to try to reformulate the physics in such a way that doesn't make such heavy use of those concepts. All right, so those are some very highfalutin reasons for, now, these basic rules, locality and unitarity, together, they define quantum field theory. The words quantum field theory are putting in unitarity and locality. So quantum field theory is the very embodiment of our usual way of talking about locality and unitarity. So the general program here is to try to figure out some other way of thinking about quantum field theory, which doesn't make such heavy uses of locality and unitarity. Now, as I said, but makes other things manifest and has locality and unitarity somehow as emergent ideas. Yes?
Nima, as part of your motivation, would you like to mention a concrete physical setup which you would like to be able to predict?
Well, I'll be mentioning it throughout the rest of my talks. Okay, and that's just what I'm getting to in a second. These are some very highfalutin motivations. I could have skipped all of this and just jumped directly to more concrete motivations, but I like the highfalutin ones. And I like them partially because they dovetail so nicely with the concrete ones. And I think that the fact that highfalutin and concrete things dovetail seems to me to suggest that this is a fruitful line of attack. Okay, so are there any concrete hints that there's something wrong with our usual way of thinking about quantum field theory? Well, of course, in the last 20 years especially, we've learned that quantum field theories do extraordinary things. You know, a long time ago, we had no idea what field theories did at strong coupling, or very little idea what field theories did at strong coupling. Then miracles happened. Dualities occurred. And we found that sometimes they had other weakly coupled descriptions. Sometimes you had two strongly coupled descriptions of the same physics. Theories with multiple classical limits. The most extravagant thing of all is to have a theory of a gauge theory turn into gravity. So these are all extraordinary things. And the fact that they all happen, and none of them are obvious when you write down, you know, negative trace, quarter trace f mu nu squared plus matter terms, but it just sort of pops out of the answer, was taken by some people as perhaps a hint that there is something, that there should be some other way of thinking about field theory that makes these amazing properties more manifest. But I think it's fair to say that those things, they're totally extraordinary, and I personally believe they are very strongly hints that all by themselves that there should be a better way of thinking about things. But another thread has been developing over the last 20 years or so, but sort of crescendoing more in the last decade and the last 5 years, which in a sense invades quantum field theory, the usual formulation of quantum field theory, in its home territory. Okay? The home base of the usual way of doing quantum field theory, what Feynman and friends handed down to us 60 years ago, was just perturbation theory to calculate scattering amplitudes. What the heck else is the usual formulation of quantum field theory good for? That is bread and butter. That's what it does. That's what we, you know, should do to compute standard model processes at accelerators, except it's too complicated, as we'll come back to in a second. But even there, you would think there can be no better way of thinking about quantum field theory than just that. And yet, as I'm sure you heard from Zvi, people discovered for entirely practical, pragmatic reasons of actually having to do these damn computations for colliders. Feynman became famous for being able to calculate 2-to-2 scattering amplitudes on the back of an envelope when it took other people 6 months using old-fashioned perturbation theory. That was a spectacular accomplishment. But Feynman didn't try to compute 2-to-3 scattering amplitudes or 2-to-4 scattering amplitudes. And then people needed to. People needed to for practical reasons to compute backgrounds at hadron colliders. And then the hell began, as I'm sure Zvi told you. Even the 2-to-3 process, you open up Peskin and Schroeder, it's 30 pages. The 2-to-4 process, it's 200 pages, 100,000 terms. Okay? It's completely ridiculous. And you might have thought that it's totally ridiculous because it looks complicated, because the answer is complicated. That's, I think, a totally reasonable attitude. And incidentally, if the theory was phi to the 4 theory, and not gauge theory, some crappy scalar theory, the answer would be as complicated as it looks from Feynman diagrams. Okay? But something extraordinary happens for the physical theories we care about, gauge theories and gravity, which is the answers, which in the beginning people calculated using a whole bunch of tricks, end up being radically simpler than you would expect. I mean, you see, you might think the answer is complicated just because you take the space-time picture as given by Feynman diagrams very seriously. It's complicated because a heck of a lot of things can happen when two gluons hit each other and go into three gluons. They can hit this way, they go that way, then split, and you've got to sum over all these things, and there's a huge number of things happening, so of course there's lots of terms. That's why it's such an extraordinary surprise that the final answer ends up being shockingly simple. These simple Park-Taylor cases of MHV amplitudes, as VM showed you, just a single term. By now we understand all tree amplitudes. And in fact, for n equals 4 super Yang-Mills, in a certain sense, we understand the whole loop integrand at least. But certainly let's just stick with tree amplitudes, which are even there, the same for good old-fashioned QCD. The final results are astonishingly simple compared to what they look like. And so, now, why is it that Feynman diagrams make the answers complicated? Is it some minutiae of some problem with, I mean, is this some technical problem? It's absolutely not a technical problem. It goes right to the heart of what quantum field theory, the usual formulation of quantum field theory does in order to make locality and unitarity manifest. To make locality and unitarity manifest for particles of spin 1 and higher, we have to introduce huge amounts of gauge redundancy into our description of the physics. And that's all that gauge redundancy that we get used to in the books with ghosts and all this stuff. It's all of that which is actually at the heart of the problem. Even at tree level, you don't forget about the ghosts. It's all the gauge redundancy. That's why you have like 100,000 terms. And you're dragging all this unphysical baggage around with you that cancels neatly in the final answer. What is that baggage for? It has a purpose in life. It makes locality and unitarity manifest. That's why Feynman is famous. His diagrams allow you to see term by term locality and unitarity. That's the whole point. Okay? But that's clearly coming at a cost. It's clearly coming at a cost of obscuring greatly the simplicity of the final answer. So this is a second hint, much more concrete. There are these highfalutin reasons that we suspect there should be a reformulation of quantum field theory. Then there's this very concrete reason just in the structure of the answers. The structure of the answers are begging for another formulation of the physics where locality and unitarity won't be manifest. Now,
but it's not quantum.
Huh?
You wanted to change quantum mechanics, but these issues are even not quantum.
That's right. Yeah, even at tree level, it's not quantum. Well, I mean, give me 5 more minutes. I've already gone over my limit. Once we start seeing concretely what things look like, I think a lot of things will become a little clearer. Okay, now, so anyway, as I said, there's been a lot of progress over the past couple of years, actually past decade, 5 years, more and more, and a lot of work has focused on n equals 4 super Yang-Mills. In the planar limit as the kind of sort of simplest theoretical laboratory where we can start talking about these things. And I just want to remind you about something which is even non-supersymmetrically true at tree level, but is true to all loop order for n equals 4 super Yang-Mills, which is not only that the answers are much simpler than you would expect from Feynman diagrams. That might be a subjective measure, simpler, although when you go from 100,000 terms to 3 terms, that sounds like progress. Okay? Let me mention one more specific thing. Zvi talked about the BCFW recursion relations, right? So did he write down the answer for, I don't know, the 6-particle next MHV amplitude, some concrete formula? Did you see a concrete formula like that? Well, okay, I'll tell you if he probably did. But the remarkable thing that happens is, let's say we talk about the 2 to 4 process. So we're talking about amplitudes where in components there's 3 plus and 3 minus helicities. These are the next MHV amplitudes. Like I said, 200,000 terms, but the result is expressed using BCFW as a sum of 3 terms. Okay? Incredibly simple sum of 3 terms. Not only is it simple, but there's something more remarkable about it, which is that each term individually isn't local. Manifestly not local. It has a structure of poles which cannot be given a local space-time interpretation. Okay, so even more, you get this feeling that you sacrifice locality and you gain something. You gain some astonishing simplicity of the results. And actually, once you start even playing with these BCFW objects, you start realizing they have an amazingly combinatorial feeling to them. They satisfy mysterious identities. They seem to be objects that are triangulating something. You can start playing with them in a way where you never actually have to start talking about what the objects actually are, but they start just playing around with labels and things like that. That's how a lot of this business that I'm going to be telling you about began, was just by pattern recognition and playing around with the properties of terms of the BCFW recursion relation. But most primitively, it's striking that the results are so simple because they aren't local. Yes?
So what's actually not local about those tools?
Well, so if you look at a typical term in BCFW, might have something that looks like that in it. I hope I'm using Zvi's notation. Is that, can everyone see that? So is this the notation using angle and square brackets? Okay, all right. So a term like this isn't local. Okay, I invite you to verify this. What is local? Something local is something that would look like some sum of the momenta. That is local. Okay? A pole like that is local. It corresponds to, in position space, something that's just propagation, propagation from point to point in space-time. That thing is not local. And if you want to verify it explicitly, if you sort of rationalize it by multiplying it by its conjugate, it would have a structure of roughly, I'm being schematic, something that looks like that. Okay? It's not local. Okay. All right. So, but let me say that the kind of final thing that pushed certainly everyone I know over the edge into thinking that there's got to be another way of thinking about things is not just that the results are simple, but that they exhibit hidden symmetries that are completely invisible when you write down the Lagrangian. Did Zvi talk about dual conformal invariants? Okay, beautiful. So you've all seen this. You've all seen this polygon, right? When the external particles are ordered, as is relevant in the planar limit, we can draw this external polygon. Did he draw this polygon or not? Okay, great. So let me just go over this in a second. So the object of interest is the n particle scattering amplitude. It depends on the lambdas and the lambda tildes of the external particles, as well as these Grassman variables that keep track of the helicity information. Did he talk about the Grassman variables? Okay, well, I'll say just, I'll get to more details in a second. Just trust me that these keep track of the helicity information, okay? So always in my talks, A is going to run from 1 to n of the number of external particles. And okay, so anyway, this is the object that we're interested in. And in the planar limit, we can strip off color factors. And then we're talking about a given color-ordered amplitude, as I'm sure he talked about. And so that means that these particles are naturally ordered. They're naturally ordered around a circle, 1, 2, 3, 4, up to n. Okay? Now, because they're ordered around the circle, you might be inspired to draw this little picture. So I'm going to draw a funny picture. I'm going to draw each momentum for particle P1, then P2, then P3, and lie them end to end on a 4-dimensional piece of paper. Okay? Because of momentum conservation, this polygon closes. Okay, this is a closed polygon. Now, the scattering amplitudes have an obvious symmetry, which is conformal invariance, because it's a conformal theory. But what people discovered experimentally around 5 years ago, by experimentally I mean by doing computations, all the data, this is an incredibly data-rich business. There's a massive amount of data, but all the data is theoretical. You know, it's the best kind of data. It's obtained by your friends who are theorists. You trust them, you know, they get it right. They present the data in exactly the form you want, you know. And if they don't do it, you can sit down and get it yourself. You don't have to beg Congress for $10 billion. You just have to beg grad students for 10,000 hours of grad student time, maybe. But, so anyway, this was discovered by staring at data, staring at theoretical data of actual computations. And people discovered this remarkable fact that the scattering amplitudes have another conformal invariance, which is under conformal transformations in this space, in this X space. So I write each momenta as, so I write this coordinate as x2, x1, xn, and so on. I can write each PA as xa plus 1 minus xa. That manifests that they go around this polygon. And the scattering amplitudes are invariant under conformal transformations in this space. So this is a totally different space whose units are momenta. It looks a lot like T-duality, right? It looks like there's sort of two different spaces. There's the original space-time. There's another space-time where the momenta are these little null edges of a polygon. And the theory has the conformal symmetries of both spaces. And in fact, the conjecture was made around 4 years ago, which now has been proven and both refined so it's exact and proven, is that the object that in the original spacetime you call a scattering amplitude, in this dual spacetime you call the expectation value of a Wilson loop, whose edges are given by that null polygon. So this is a really amazing thing. You're in the first spacetime and you say, here there's a bunch of functions of momenta of the external particles. And damn, I know they're scattering amplitudes. Look at that. They look exactly like amplitudes. They have the kind of poles we expect of amplitudes. They factorize the way amplitudes do. And there's someone in this totally other spacetime who says, wow, this thing sure looks like an expectation of a Wilson loop. Okay? They're exactly the same functions. They have exactly the same properties. Okay? Yes?
You said before that those theories in this system are easier than Untitled Chapter.
Yes, yes.
Why? Can't you do just the same tricks in Untitled before?
Nope, nope. Well, maybe I can defer this discussion a little later. Actually, you can, but only when phi to the fourth theory is embedded inside supersymmetric theories. That lets the crappy scalars inherit the good properties from the high spin particles. Okay, it's exactly backwards. But you see, this is another qualitative thing that indicates that there's a new way of thinking about things. Because why is phi to the fourth theory the first thing in the books? Because it's the easiest way to talk about local quantum field theories. It's the simplest example, right? But that's the way normally dual descriptions work. Things that are easy on one side will be hard on the other side, and vice versa. I'm not saying there won't be some dual formulation of phi to the fourth theory. I'm saying that won't be the place to discover it. The place to discover it will be from interesting theories, from gauge theories, and even probably gravity. But anyway, we'll mostly be talking about gauge theories. Anyway, so this is a symmetry that even the tree amplitudes have. It's a symmetry that could have been discovered by Yang and Mills in 1955. Of course, they would have to develop a lot of technology to actually compute these things, but everything was sitting there. It's really possible to calculate these diagrams. You didn't need to go, so you didn't need to just really sit down and just calculate amplitudes in these theories. It's a property even of the tree amplitudes. And it wasn't discovered till 2007. Okay? That shows you there's things that are lurking right under our noses, not in some far-off place of strong coupling or some magic thing. The things lurking right under our noses in the structure of this marvelous thing that was handed down to us by our intellectual ancestors in the early 20th century, but which seems to have properties that they never dreamed of. And I think trying to unearth them and understand them from another point of view promises to teach us a lot. Probably most grandly, it might give us a different picture for what space-time and quantum mechanics really are. Okay, so as I said, but there's a symmetry which is utterly invisible in the Lagrangian. And the final comment I wanted to make is that these BCFW terms, they turn out to be term by term invariant under this symmetry. In fact, the BCFW terms are the objects that are invariant under all the symmetries of the theory. This conformal and dual conformal invariants together generate this infinite dimensional symmetry algebra known as the Yangian. Did Zvi talk about the Yangian? Okay, so there's this infinite dimensional symmetry algebra known as the Yangian. And the BCFW terms and many, many other terms, and that'll really be the topic of a lot of the rest of these lectures, are term-by-term invariant into them. They're the building blocks that have all the symmetries. They're not local. They obviously can't be local because they don't give a crap about either space-time. They just care about representing the actual. They're the things that know about all the symmetries but aren't making any commitment to one local description or another. Okay. Okay, so just a very brief snapshot of the progress of the past even couple of years. For n equals 4 super Yang-Mills, in the planar limit, part of the problem is, in a sense, solved. The part of the problem which traditionally is summing up all the Feynman diagrams, okay, which already at tree level is a horrible nightmare and at loop level is a monstrous nightmare, at tree level was solved by the BCFW recursion relations. And at loop level has also been solved by an extension of these BCFW recursion relations to all loop orders. Okay? So in a sense, if you want to sum up all the Feynman diagrams, or if you want to have the integrand, the thing that you have to integrate to get the amplitudes, that's a solved problem. It's a 2-line code in Mathematica. You can press return and have the 17-particle, 4-loop, n to the 5th MHV amplitude sitting on your laptop. Okay? So there's no conceptual or any other practical obstacle. That part of the problem is actually done. The ideas that went into doing that are very closely related to the theme of the rest of my lectures. Well, I'll come back and mention them as we go along, but that part is done. A lot of the attention just over the past 6 months to a year has moved towards actually trying to compute the integrals. And in the process of computing the integrals, further remarkable things show up. Further dramatic simplifications happen. And if you calculate things at one loop in field theory, even at one loop, you get logarithms and dilogarithms. At 2 loops, you get more complicated polylog functions and so on. And there's a whole rich and remarkable structure to these polylogarithmic objects that are related to some very deep areas in mathematics, which are also related to some of the other things that I'll be talking about in these lectures. And anyway, that's another line of progress over the last 6 months or over a year, as people are starting to learn how to do the integrals and actually see what the final answers look like. But what I want to focus on, and what I've myself been the most excited about, is that we're starting to see some really new, very beautiful mathematical structures that seem to be lying at the heart of this business. And that's what these other words, the positive Grassmannian, are about, and I want to tell you something about. Now, I'm trying an experiment in these lectures. So it's really impossible to review this whole subject in 3 lectures or 4 lectures or 5 lectures. And certainly not in 3. So I've decided that what I'm going to do is the following. So today I'm going to tell you some very basic things that you will need to know no matter, if you're interested in the subject, you'll need to know no matter what. And they're just a good set of things to know about the right way of thinking about symmetries, twistors, very basic things about Grassmannians and so on. But they're very much starting off from thinking about the physical problem. Over the next 2 lectures, what I want to do is start from the other end. I think things are starting to come to a point of being understood well enough that it's almost possible to start from the other end. Start from a new set of sort of principles or pictures or whatever you want to say, and start building back towards constructing what is going to what's going to in the end be the actual amplitudes. So that's what I'm going to attempt to do in the 2 lectures tomorrow. Is forget all about the physics. Start from some very nice, simple combinatorial objects, and start building up pictures associated with them that look an awful lot like Feynman diagrams or certain other kinds of diagrams. And then before long, we'll see that we've invented the entire S matrix for n equals 4 super Yang-Mills. Starting from very, very primitive starting points in a way that makes all the symmetries manifest and many, many other things manifest as well. Okay, so that's the plan. I should say that the picture that I'm going to be telling you about in the next couple of days is not in the literature. This is something that, the whole subject is something that we've been thinking about with collaborators for 2.5 years or so, and really intensively for the past 1 year. And in the past year, at 3 separate occasions, we thought we understood it, basically very well. In April, in August, and well, now. And in April and August, we were wrong, and now I think we are right. And now, but part of the reason I say this is, I said that there are some remarkable new mathematical structures that are showing up. And we finally found the mathematicians who happen to have been thinking about exactly the same problems accidentally, remarkably, just over the past 2 or 3 years. So these really are new mathematical objects that even are interesting and new to the mathematicians. And as usually happens in this kind of situation, we learned a lot from them, but physics is teaching both of us, both us and them, a lot more about the objects, certainly than they ever dreamed. And also, anyway, but we got enough out of them that I think we're definitely at a local maximum of the understanding, so it's worth spending the 2 lectures tomorrow telling you what that local maximum looks like. Well, I'll just make one more comment, which is interesting. The ideas that are involved are of a very different part of math that then has made contact with quantum field theory over the past 20 or 30 years. I mean, very, very roughly, the kind of mathematics that's made contact with quantum field theory in the past 30 years is the kind of mathematics Atiyah loves. The kind of mathematics that's showing up here is the kind of mathematics Grothendieck loved. Okay? And these 2 strains, even in mathematics, have not really played nicely with each other. It's really remarkable to see the Grothendieck side of the story showing up so primitively in N=4 super Yang-Mills. Yeah? Sorry? I know what happened to Grothendieck, and I'm very worried about it. But the Pyrenees sound nice to me now. It's, okay. So, all right. So let's get going. So that took much longer than I thought, but shorter than it could have been. So, all right. So let's cut the bullshit and get down to work. So what I want to do in the rest of this lecture is, as I said, get some very, very, very important and basic ideas out. And most of this is going to be, we're going to start by just talking about some of the symmetries of N=4 super Yang-Mills. And actually, we're going to first start off talking about conformal symmetry in general. So the theory is a conformal symmetry is a dual conformal symmetry. So we had better get used to talking about these symmetries in the simplest possible way. It's an overarching theme of this business is you want to clean up the kinematics as much as possible so nothing is obstructing your view into the dynamics of what's actually going on. So we want to come up with the simplest, nicest possible variables. You've already seen the lambda and lambda tilde variables, right? So the momenta, we normally, this is already big progress to write each momentum as a lambda and a lambda tilde. The spinor helicity variables. But now I want to talk about the symmetries that, the variables that make thinking about conformal symmetry as simple as possible. And this is going to immediately get us to a discussion of twistor space. Okay, so let's first just talk about ordinary conformal symmetries. So this should be reviewed to many of you. But the juicy part of conformal symmetries, there's Poincare and scaling, but the juicy part of conformal symmetries are inversions, okay? Or the special conformal transformations. And if any of you don't know what an inversion is, you actually do know what it is if you've ever solved the problem in undergraduate E&M of finding the electric field outside a grounded conducting sphere. Okay? When you solve that problem, you use a method of images. And in the books, they tell you to put some image charge here with some intelligently designed charge at an intelligently designed location. And then you find amazingly that that image charge makes the surface of the sphere be equipotential. And every time one of those tricks happens in E&M books, it's because of a symmetry. In this case, this is just, it's using the fact that, the theory is conformally invariant, and we're using inversions to find a second solution with exactly the same value on the sphere. Okay? So inversions are the symmetry under x mu goes to x mu over x squared. So that's the exciting part of conformal transformations. So theories that are conformally invariant have many kinds of generators. So of course we get the special conformal transformations by inverting, doing a little translation and inverting back. So that's the infinitesimal version. And already something should bug you. And again, this is something that's a property of any Lagrangian, any usual way of talking about field theory, is that we have these symmetries, translations, Lorentz, and conformal, and they look like very, very different generators, even though they're all just one big group together. Translations look like ddx, Lorentz and looks like x ddx, and conformal transformations looks like xx ddx. Okay? So it's just strange that all these, they're all just, after all, symmetries, and yet we're treating them all on a very different footing. Okay? So it's very nice to find variables that, that make the action of conformal symmetry as simple as possible. Well, one key observation is that if we take 2 points, x and y, and if I look at the invariant difference between them, x minus y squared is, of course, not invariant under inversions, but it goes to x minus y squared over x squared y squared. Okay? Okay, so that's what, so of course the distance isn't conformally invariant. It's not even scale invariant. Okay? But you notice that if x and y are null separated, then so are their images under inversions. So null separation is a conformally invariant idea. Okay? This was one of many motivations that Penrose had for thinking about twistors. Actually, his real motivation, this is a technical motivation and is the one that we're going to be mostly focusing on, but his real motivation all the way back in the 60s, there are 2 people in the 60s, as far as I can tell, who really understood very well the sort of basic idea that the observables in gravity are associated with the boundary, so you should go to the boundary. Bryce DeWitt understood it very well, and Penrose understood it very well, and this was really his motivation for thinking about twistors. So the idea is that instead of talking about points in space-time, you talk about whole null rays through space-time. Okay? And a null ray in space-time goes out to the boundary and has a better chance of being variables in which you could, more proper variables to talk about boundary observables like scattering. Okay? Okay, now, so let's do that. So if we have a null ray in space-time, it's going to, it'll be a null ray under inversions as well. It's a nice conformally invariant idea. Okay, so let's do it. How do we write down a nice equation for this null ray? I should also say that we're unapologetically complexifying everything. Okay? So lambdas and lambda tildes are independent complex variables. The real momenta correspond to lambda tilde being the complex conjugate of lambda, but we're going to just imagine complexifying everything. All right. Now, let me just pause for a second. I'm going to make it seem like it's all completely trivial, which it is. But I just want to say one thing, because there was a nice point here. Let's just think about the space of first real null rays in Minkowski space. The space of real null rays in Minkowski space is a 5-dimensional space. Okay? Why is it 5-dimensional? First, you take your laser beam, and you can point it in 2 directions corresponding to the angle on the sphere. Okay? And then the origin of where that is, you can pick relative to any coordinate axis. So there's 3 coordinates that specify that. Okay? So the space of real null rays in Minkowski space is 5-dimensional. Okay? If you naively complexified that, you'd have a 5 complex dimensional, 10 real dimensional space. Okay? That's a perfectly legitimate thing to do and is not interesting. Okay? What is interesting is a much more economical complexification of it, which is what Penrose found. and what we're talking about. Penrose found a complexification for the space of null rays, which is 6 real dimensional, 3 complex dimensional, and that's just what we're going to talk about. Okay. All right, but let's just be super dumb, right? We want to write down an equation that defines a null ray. So here's the equation. Yes.
The silliest of the questions. Could you please write how are you calling those objects?
Which object?
Those null rays?
A null ray. Yeah. Oh, you mean you want me to write it here, a null ray? Oh, well. You want to come up here and annotate as we go along? Is that better? You really couldn't have just put that on your own piece of paper, huh? You know that? Okay, that's great. Yeah. Okay, you're welcome. Glad to oblige. Okay, so we're going to write down this linear equation. Okay, there's a linear equation. It clearly defines a line. It's a linear equation for the x's, right? Mu and lambda are data. They're parameters. I just hand you a 2-vector mu with a dot index and a 2-vector a lambda. Okay, that's data. And then I look at all the x's that satisfy that. Okay, claim is that all the x's that satisfy that define a null ray. Let's first of all see why it's null. See why it's null. Let's say I have 2 points on the same line. So with the same mu and lambda, right? There are 2 points on the same one. So let's subtract. That means that x1 minus x2 lambda is equal to 0. Right? But that means that x1 minus x2 has a vanishing eigenvector. So the determinant of x1 minus x2 is equal to 0. But this is nothing other than just the invariant distance between x1 and x2 squared. Okay? So any 2 points on these lines are null separated from each other. Okay? Great. So let's group mu and lambda together into a little 4-dimensional vector. Okay? I don't know, I could say this has an index I that runs from 1 to 4, although it doesn't matter. Okay? So right now what we've seen is if someone hands me this 4-dimensional vector, associated with that is a null ray in space-time. Right? Well, actually, not quite, because obviously if I multiply this equation by any constant, I get the same null ray. It's the same equation. Right? So that means that this is still redundant. I should identify z with any constant times z. So if you hand me a 4-vector up to an overall scaling, that's what's in correspondence with a null ray. Okay? Yes? Sorry? Y is what 0? Y is everything that's 0. Okay. This is just my pulled from thin air, although it's not so thin, pulled from moderately thick air. Linear equation. I'm just trying to write down some linear equation for a bunch of points x in space-time. Everything is nicest when we work with these spinor helicity, well, with these AA dot coordinates. So I'm writing down an equation for x AA dot. That's the dumbest thing I can do. This is just the dumbest thing, which is a linear equation in x AA dot equals 0, right? So the claim is that if I use this to define a bunch of points x in space-time, that any 2 such points are null separated. And we got that point by writing the equation down for 2 different x's, subtracting them and seeing that, thought of as a 2-by-2 matrix, x1 minus x2 annihilates lambda. That means that this 2-by-2 matrix x1 minus x2 is vanishing determinant because it has a vanishing eigenvector, and the determinant is just x1 minus x2 squared. Okay? Okay, so what we really see then is that we have a point now in CP3. So these 4-dimensional vectors up to a scaling is just CP3. If CP3 scares you as it scares me, always think of it as a 4-dimensional vector up to a, and just anything you do with that vector should be invariant under rescaling it by a constant, okay? And then you'll never get it wrong. Okay, so here we're starting to see the first part of the correspondence. A point in CP3, the z's, corresponds to a null ray in space-time. So this is twistor space, TS. This is space-time, ST. Okay? Right? That's the first part of the correspondence. Any questions about this? Yes?
I have a question about something that you mentioned before.
Yes?
What do you mean with a dense matrix of a conformal invariant?
Oh, we'll come back to that. Okay. In fact, yeah, so this was an old question that people used to pillage our poor Amplitudes friends with 10, 15 years ago, and it's a totally dumb point. There's a perfectly well-defined notion of what, well, we'll come back to it later. But rest assured, it's a completely stupid point. It's, yes?
Where can we find this? Where can was mentioned that?
Where can, I mean, there's any one of hundreds of books on twistors. But please don't read any of them, okay? Just, I'm really trying to tell you, what I'm about to tell you is every single thing you need to know about twistors, okay? You don't need to know nothing more than what I'm about to tell you. At least to work in this business at the level that I work. Maybe you want to be much better, which is not hard. But you don't need to know, what I'm telling you is everything which is actually needed. Yes?
What are the components of
Z, well, just that. It looks a lot like a Dirac spinner. Huh? No, Z has 4 components. If lambda has 2 components and mu has 2 components. Okay? Yeah, 2 spinners. So Z itself lives in C4. Okay? So, but Z up to equivalence lives in CP3. All right, now comes the next interesting part of the equivalence. Let's say I have 2 points in twistor space. Oh, actually, before I do that, let me mention one last thing. Sorry. So this is already, it's very pretty, but it does something else. Conformal transformations act trivially on the z's. Conformal transformations are nothing other than, let me put it here. Conformal transformations are nothing other than SL4 acting on z. So we've succeeded in finding variables that trivialize conformal transformations. They just act as 4x4 linear transformations. Okay? This is indeed a projective space. It's not just that the points are equivalent up to rescaling. Everything is projective. There's no metric. There's no distance. All we have is projective geometry in the twistor space, in this CP3. Okay? That means concretely, if you do anything with these z's, they have these indices, I, so let's say I have a bunch of z's, z1, z2, z3. Anything sensible, any sensible formula I write down with these guys can only involve the epsilon symbol. Okay? So the symmetry is just SL4. Yes, Zara? Yes, there is. It'll be very natural in just a moment. So this is really the equivalence between the well-known equivalence. It's the same as the equivalence between SU4 and SO6. It turns out that it's still always more natural, especially when you're talking about fermions or things that carry spin in general, but really fermions, to always work with SL4. That's right. So you could think of it in 6-dimensional language if you like, but then you have to deal with spinor representations. So it's more convenient to just work with this simple 4-dimensional representation. But you're absolutely right. OK, now let's see why this is, by the way. So what's Lorentz? Lorentz is obviously SL2 cross SL2 acting on lambdas and mu's. Okay, so that's the obvious thing that we know and love. But let's see something exciting, like what are inversions? Well, take this equation and divide by the determinant of x, which is x squared. Get exactly the same equation with mu and lambda interchanged. So inversions are nothing other than just interchanging mu and lambda. It's trivial linear transformation on the lambdas and the mu's. Okay? Let's look at translations. What are translations? Translations are x goes to x plus d, right? Well, that's nothing other than shifting mu by something proportional to lambda. Okay? So that means that if I think of this SL4 as a 4x4 block, here's SL2, here's SL2, and up here are special conformal transformations randomly, and down here are translations. Okay? So it's just simple SL4 transformations acting on this guy. Okay? Never again do you have to remember the generators for K and all that stuff. It's just all SL4 in this space. All right. So let me keep going. So that's going to, of course, be incredibly useful. But let's go to the second interesting part of the correspondence. Let's say someone hands you 2 points in twistor space. I don't know, let's call the points ZA and ZB. Okay? ZA corresponds to some line in space-time, and ZB corresponds to some line in space-time, null ray in space-time. And those null rays intersect at a point. Now, you might complain that, well, 2 null rays don't in general intersect. That's 2 real null rays. 2 complex null rays do intersect at a point. But you never have to visualize anything in this business. It's so easy to just be very explicit. I mean, if it hurts to visualize. It's just trivial to see this very explicitly. Okay? So let's write down the equation for the first guy and the second guy. So I have mu A minus x lambda A equals 0, and mu B minus x lambda B equals 0. And let me put the annoying indices on here. Oh, sorry about the A's. Well, you'll forgive me. No, you won't. Okay. Okay. And what I want to do is see, is there a point on both of them? So I want to see, can I simultaneously solve both of these equations? Well, I can. This is 2 equations. Well, this is 2 equations here, 2 equations there. It's 4 equations in the 4 unknowns x, so you can solve for them. And a trivial exercise to do it. You just multiply this by lambda b, that by lambda a, and subtract. And you find an explicit formula that xa a dot is mu a lambda b a dot a minus mu b a dot lambda a divided by lambda a lambda b. So that's an explicit solution. Okay? That shows you that 2 points in twistor space, the corresponding null rays intersect at a point in space-time. Okay? But once again, notice that I can take any linear combination of these 2 equations that I like, and it would specify the same point. So that means that I can do any GL2 transformation that I like on A and B and define exactly the same point. Doing GL2 transformations on A and B will move the point A around and move the point B around. But it leaves the line that connects them in CP3 invariant. Okay? So we've learned the second piece of the correspondence, that a line in twistor space with here's 2 representative points on it, but really it's the whole line on twistor space is associated with a point in space-time. That's the first correspondence, and this is a point in space-time x, which you can say depends on A and B, and for which we just gave the expression a second ago. Okay? All right. So everything that you might like, we have a correspondence for. Now, let's say we happen to be interested. So let me just say a couple of little technical things. We're interested in conformally invariant theories, but we might be interested for a variety of reasons in non-conformally invariant objects. And you see actually right here, even in writing these equations down, we've made some artificial distinction between the top 2 and the bottom 2 components of Z. Okay? So another way of saying it is that the Poincare group is some subgroup of SL4, which leaves some tensor invariant. Okay? This tensor is called the infinity twister. And its definition is just that I mean, it's just a thing that looks like epsilon, let's say 0, 0, 0. Okay? So this is a 4 by 4 matrix, and this thing leaves only the Poincare part of the full SL4 invariant. Okay? The point is that if I take Z1 epsilon Z2, Z1 I Z2, this is otherwise just lambda 1 lambda 2. Okay? So if I want the usual angle brackets, then this is breaking the full Poincare group. Okay? Now notice too, this line in twistor space, I can also associate with an antisymmetric tensor, right? Because it's invariant under GL2, so I take a ZA, ZB. Antisymmetrized ZA, ZP is invariant, projectively invariant under this GL2. So lines are associated with antisymmetric tensors. Okay? So that infinity twister is a special line in twistor space. So if we want to break Poincare symmetry, if we want to break SL4 down to Poincare symmetry, what we do is pick a special line in CP3. Okay? What is that special line in CP3 in space-time? It's a special point. And it's a point at infinity. Okay? It's the other one. Okay? I call it the infinity twister. Okay? That's a big hint. That's not the zero twister. But anyway, but they're conformally equivalent, so maybe that's okay. So yes. So and of course that makes sense. So we needed to add this point at infinity to conformally compactify Minkowski space. And so that's it. So that point at infinity corresponds to a line in twistor space, and that's this infinity twister. Okay? That's one thing. Yes?
But when you compactify Minkowski space this way, you will end up in a sphere.
Yes. That's what it is. That's the conformal compactification of Minkowski space, indeed. Okay. Now, one more thing is I said that the conformal group here is SL4 because I was complexifying everything. Yes?
SL4 is SL4 C or
C. Everything is C here. Everything is C. Okay? Everything is going to be C until tomorrow when everything will be R. But no, I'm kidding. A little bit. Yeah.
conformal group is just smaller than.
Yes, that's just what I'm talking about. So this is the complexified Lorentz group. So let's say this slowly again. The real Lorentz group is SL2C. The complexified Lorentz group is 2 copies of SL2C. Okay? There's a SL2 that acts on the lambdas and an SL2 that acts on the lambda tildes, if you like. Okay? The complexified conformal group is SL4. And by the way, since everything is complex, it's so nice to just think about these SLs all over the place, right? Everything is projective. We're in projective spaces. There's all projective geometry. It's just wonderful. Okay. But if we want to come back to reality, both figuratively and metaphorically, we can ask what. So the real conformal group is a subgroup of this. Okay, which subgroup of it is it? Well, it is a subgroup which leaves. It is the subgroup which leaves the 5-dimensional. So this is we have a 6-dimensional space here, right? Remember, each one of these z's, a point in CP3, 3 complex dimensional, 6 real dimensional. Okay, these gives us complex null lines. The real part of Minkowski space, those are the real null lines, and we just counted them. They're 5-dimensional, right? There's a 5-dimensional space of real null lines. So that means that we have to find there is some Hermitian form which is left invariant and only preserves that 5-dimensional real null lines. And that Hermitian form is exactly the one that you are familiar with from the bar of Dirac spinners. Okay? So the reality condition on let's say a point in twistor space that corresponds to a real null line is that z bar z is equal to 0. Okay? Where if z is lambda mu, z bar is literally mu star lambda star. You can easily check that if you look at the point now associated with that, anyway, you can very easily verify that these correspond to real null rays. Okay? And so it's that subgroup of SL4 that leaves this particular Hermitian form invariant. Okay? I could write that the other way as 1 minus 1, and that makes it clear that it's an SU2, 2 subgroup of the SL4. Okay? And that is indeed the real conformal group, is SU2, 2. But you never have to worry about these commas and all this crap when you go complex. Okay? Everything is just SL, and it's just beautiful. Okay? But as I said, it's just the last bit of, and this isn't going to matter a lot until the very, very end if I get to it. But if you look at any of the old Twister literature, you'll see a picture that looks like this, which is a sort of a sphere cartoon of the situation in Twister space. This is what it would be if it was CP1 rather than CP3. CP1 is a sphere. Okay? It's a two-dimensional space. The equator is like the real null lines. Okay? But now this whole thing is really six-dimensional. But the space of real null lines really does divide Twister space into two halves. The two halves are where z bar z is positive and z bar z is negative. Okay? So you'll see pictures that people will call these things PT plus, PT minus, and PN. This is a five-dimensional space of real null lines, which breaks Twister space up into two pieces, okay? Positive and negative. Anyway, it's not going to be very, very important. So you can mostly ignore all this reality crap and just think about things complex. Yes?
So this corresponds to these very favorite 4 dimensions.
At the moment, yes.
Or even dimensions, but what could you do in 3 dimensions?
3 dimensions, yeah. You'll see a little bit. Yeah, not this literally, but something very nice does happen in 3 dimensions. Well, I might mention 3 dimensions and ABJM in particular tomorrow. You'll see ABJM is a very small part of the big structure that I'm going to be telling you about tomorrow. So it is actually covered, but not in this tutorial way, but in a closely related way. Yes?
I want to ask about the correspondence. Did you actually find that any 2 null rays intersect?
Yes.
That's kind of non-intuitive for me, because if I just translate null ray, how
Yes. So the reason is that you're thinking about this naive complexification and not this CP3 complexification. Okay. So this 6-dimensional space, 6 real dimensional space of null rays has this nice property that any 2 of them intersect. You're right. If I take 2 completely random null rays, they don't intersect. But the null rays that are covered, the particular complexification of the space of null rays is given by twisters. Any 2 of them intersect, and we just found it explicitly.
But in the end, it's just null rays in space-time. Right?
Yes, it's complex null rays, complex. So it's 2 real dimensional. That's what gives it a hope, right? Two real dimensional ones could intersect. It's still not guaranteed, okay? But the ones that we get from Twister space always intersect.
They still live in 4-dimensional grid space.
No, they live in 4-dimensional complex space. It's complex. I mean, they're 2 real dimensional. They live in a 4-dimensional complex space. 8 real dimensional space. Yes?
Is it coincidentally related to the Rex spiders?
Sorry?
Is it coincidentally related to the Rex spiders?
Yeah, I guess. Yes, coincidentally. Okay. So anyway, right. So we see that that twisters are amazingly nice variables. Twisters are amazingly nice variables to talk about conformally invariant theories. One final point. Let me just illustrate some of the, let's just do a little small computation here. Let's say I have 2 points in space-time, okay? And let's say that this point x is associated with the line AB, and y is associated with the line CD. Okay? Little exercise, compute x minus y squared. Okay? I gave you the formula for x and for y, so you should just be able to compute x minus y squared. Well, let me tell you what the answer ends up being. And let's see why it's totally obvious that it has to be this answer. Okay? So first, some notation. What do I mean by ABCD, this 4 bracket? Well, there's a 4 vector ZA, ZB, ZC, ZD, and I just contract them with the epsilon symbol. Okay? So that's the SL4, the only SL4 invariance I can build. Okay? Now, it's obvious that just with these 4, but anything I do with these variables, remember, has to be invariant into rescaling them. So the answer could not have just been A, B, C, D flat out, because that has weights under rescaling A, B, C, and D. Something has got to cancel the weights. There's no way I can cancel the weights just using 4 brackets. I mean, I could divide by A, B, C, D and get 1, but that's obviously wrong. Okay? So what soaks up the weights are the lambda A, lambda B, lambda C, lambda D downstairs. So look at this thing looks pretty crappy. It's not SL4 invariant. Well, of course not. The distance isn't SL4 invariant. Okay? But we also nicely see that when this vanishes, when does this vanish? It vanishes when ABCD is 0. And the 4 bracket ABCD equals 0 is a nice SL4 invariant statement. In fact, what is it geometrically as a statement? It's nothing other than saying that these 2 lines that in general live in CP3 intersect each other. Okay? So every conformally invariant question turns into some obvious statement in projective geometry in twistor space. So 2 points being null separated means that the corresponding lines intersect each other in twistor space. Okay? This makes it amazingly easy to visualize Minkowski geometry. And this is, to me, one of the coolest things about these variables. And it's actually useful for many concrete computations in this business. Let me give you one example. It's a sort of take-home example that you can play with tonight, although I'll give you the answer. I'll give you one example of a simple Minkowski space geometry question, which is much easier to think about and see what the answer to is in twistor space than it is in ordinary space-time. And as I say, once you go projective, you'll never go back. So let's ask the question. This is actually the simplest baby version of a question that comes up all over the place in the amplitude business at loop level. But I'll just phrase it as a little geometry problem in Minkowski space. So here's the problem. Let's say I'm given 4 points in Minkowski space. 4 general points in Minkowski space. Wow. Okay, there's 4 general points in Minkowski space. The challenge is to find a 5th point which is null separated from all 4. It's a nice little question. Okay? Now, how many solutions do you even think there is to this problem? I mean, very naively, when someone first tells me this problem, you would think, I don't know, really stupidly, maybe there's 16 solutions. Because you've got to solve 4 quadratic equations, right? X minus x1 squared equals 0, x minus x2 squared equals 0, and so on. There's actually 4 solutions. Oh, there's actually 2 solutions. Okay? But just try to even visualize the answer. You can sit down. It's not so hard to sit down and actually laboriously write it out. Okay? And actually write out the equations and solve it algebraically. But I want to translate this problem just into twistor space, just so you see how you can visualize what's going on much more easily. Part of the reason you can visualize things much more easily is that we're doing projective geometry in CP3. The C doesn't matter for visualizing things. In CP3, we can always choose coordinates, if you like, so that we can rescale the top coordinate to be 1, so that we're always dealing with, oh, crying out loud. We're always dealing with a little 3-dimensional vector here. Okay? So that means that whatever we're talking about, points, lines, things like that, we can really visualize as points and lines in real 3-dimensional space. So when you say there's a line in twistor space, literally think of a line in 3 dimensions. Some other line is some other line in 3 dimensions, and so on. Okay? Literally. Okay, so what does this problem turn into? It turns into the following problem. Each one of these things is now a line. Oh, wow. So I have 4 lines. Okay? And now the point x that I'm after is another line. And I'm now trying to find a line which intersects all 4 of these given lines. Okay? Does not at first sound like a much easier problem. Although, if any of you know anything about, if any of you have taken a baby algebraic geometry course as undergraduates, this is the very first problem in enumerative geometry. It's the classic first problem of the so-called Schubert calculus invented by Mr. Schubert in the mid-1800s. Okay? This is really the first problem. In P3, find one line that intersects 4 given lines. Okay? So let me tell you how Mr. Schubert figured it out. So the idea is, okay, this still seems a little hard, but the idea is to imagine moving the lines around until they're in a slightly less generic situation. Okay? Let's say we move them around so the lines look like this. Okay? So each one of my thumb and index fingers is a line, continued. That's a line, that's a line. Okay? So there are 4 lines. See the 4 lines? All right. So the question is now, find a line that intersects all 4. There's 2 totally obvious ones. That one and the other one, right? So there's 2 lines that intersect all 4. But now just smoothly move the lines around. So they separate. The equations are smooth. The number of solutions can't jump discontinuously. So it's always 2 solutions. Okay? So that takes a algebra problem in Minkowski space and turns it into a little pick-up sticks problem. I don't know if you guys are too young probably to have to play with pick-up sticks, but back before the interwebs, you know, we had we played these games with sticks and stuff like that. And anyway, and it goes up from there, and it's much more and the more complicated problems are much easier to visualize in this particular way. More than that, it also tells you what the solutions are. And it tells you many other things. So let me tell you actually, just to give you another example. So let's even say they're in generic position. Okay? So there's some line that intersects all 4. Okay? But now if you stare at that line that intersects all 4, and yeah, maybe to find these particular points you actually have to solve some quadratic equation in general, which you do. But there is a special line, and on that special line, there's 4 special points. Okay? But what have we found? So there's a special line. That's a CP1. There's 4 points on a CP1. What do you do when you have 4 points on a CP1? What's the only invariant information contained in 4 points on a CP1? There's a cross ratio that you can build out of those 4 points. Okay? Okay, so that's an interesting object. Given just the data of the 4 external lines, you can find the line that intersects all 4. And there should be something canonical and important about the cross ratio that's built out of those 4 points. Okay? Now, when this kind of thing is done when it comes up in the context of amplitudes, people don't use these twistor variables, and they just use standard momentum variables, and they find expressions with horrible square roots in them and very complicated kinematic stuff, which were sitting in the literature for 25 years until a few years ago people realized that they're the cross ratio of these 4 points thought of in this way in twistor space. And then the more complicated ones that arise in the more complicated cases also have beautiful geometric interpretations like this. Okay, so let me mention a final thing. Well, all right. So far we've been talking about twistor space associated with points in space-time, right? There's points in space-time. We have associated points in twistor space. Let me just complete. So far this is just math, right? You know, so which space-time it is, whether it's space-time, the dual space-time, when we're talking about scattering amplitudes, it doesn't matter. It's just any Minkowski space with a conformal symmetry and its associated twistor space. So there's a final natural object that we might want to think about, which is what does, for example, integrating over space-time look like? Okay? What does d4x look like? So this is integrating over points in space-time. So what should that correspond to? It should correspond to integrating over lines in momentum twistor space. Okay? So in integrating over lines in momentum twistor space is, well, if I'm very naive, if here's x, then I would say there's a point, there's a line, here's 2 points A and B, and I'm just going to do d4za, d4zb. Okay, this is obviously too naive for a number of reasons. First, we started with a 4-dimensional integral, we got an 8-dimensional integral, right? So, but that's okay, because remember, there's a redundancy, right? We can do any GL2 transformation we like on A and be left with exactly the same thing. So this is really d4za, d4zb mod GL2, okay? So I can give you an explicit formula for what that is in a moment, but that's a stand-in for doing the integral over the lines in momentum twistor space. But there's another problem, which is what? There's another problem, which is that this thing has weight under rescaling A and B, which it should not, right? So what could the answer possibly be? It's just 1 over lambda A, lambda B, or I can write it as A infinity twistor B to the 4th. Okay, and now everything is kosher. Oh, sorry, yeah. Is okay, yeah. I don't know the technical meaning in this context, sorry. All right? So now, let's draw something that you might encounter in computing a simple correlation function. This will, when we interpret these as variables in this dual space-time, this will literally be a loop integral. But let me just, so let's say I have a point x1, x2, x3, x4, and I have a point x, and I'm literally, with these propagators, integrating over d4x. So let's say I want to write d4x, then 1 over x minus x1 squared, x minus x2 squared, x minus x3 squared, x minus x4 squared. Okay? Just for fun, just so I write it, oh well. I'm going to defer this discussion to later. Sorry, I'll defer this to it tomorrow. It'll take a little longer to make it a little cleaner. Sorry, I'll defer this to tomorrow. I apologize. Okay, but this is correct. Notice that d4x is not conformally invariant again. Okay, but integrated against suitable objects, it'll be conformally invariant, and so we'll return to talking about what those conformally invariant objects look like. Actually, I started 10 minutes late. Can I have another 5 minutes? Okay. There's one final topic I think I can quickly talk about. So far, now let's really think about these x's as being our space-time, ordinary space-time. Okay. These twistor variables, yes.
There's our ordinary space-time, we usually think about it, is hardly conformal.
Right.
So, how do you think about, even at this stage, about real space-time, the real world, which
masses, for example,
scales.
right? Yes, right. Yeah, masses are really not so bad.
Just
yeah.
scale of mass. I mean, or mass.
Yeah. For example,
in
yeah.
general, break it up components.
Yeah, but
More than that.
it is more than that. Yeah, it is more than that. I think the conceptually hardest part is the renormalization group, and this is, I think, a really fascinating and kind of open question. I might say a little bit about it towards the very end, because the kinds of mathematical structures that I'll talk about tomorrow also show up in very, very different contexts. Anyway, one part of which is related to this Kahn-Kreimer et al. Friends' way of thinking about the formulating the renormalization group. But really, the toughest thing in this business is to understand the renormalization group, because that's the one thing which locality is God-given for and is incredible for. and off-shell things and the whole picture of integrating things out. It's clearly, that's the best physical way of understanding renormalization, of understanding the renormalization group. And so seeing how that comes out of a formulation without space-time in it is going to be a big and interesting challenge. That means there must be some really meaty and interesting mathematical structure that allows that to happen. Right, yeah. You could say that. Right. Right. Indeed. We've had this discussion before many times, yes. No. Absolutely. Absolutely. Except there's well. So let me just say a few words about this. So we're still going to have to finish some introductory things tomorrow, but these objects, or these kind of structures that I'm talking about, show up first, well, show up here in the context of thinking about amplitudes. Okay? And as I mentioned, there are these very primitive combinatorial things in algebraic geometry. They're very new, they're new to the mathematicians, and there's something very, very, very interesting about them. They show up in two other contexts, very surprisingly. One of them is in the study of wall crossing phenomenon in n equals 2 field theories. Okay? So literally the same structure, not analogous, exactly, precisely the same mathematical structure shows up in that question. Okay? That has nothing to do with planarity, nothing to do with Yangian invariance, nothing to do with n equals 4. It's something else entirely. It has to do with S-duality. Okay? It has to do really with the magic of S-duality. In amplitudes, it's really all about the magic of T-duality, roughly. You know, the T-duality in ADS. So there seems to be some gadget that's really well designed to talk about things in a duality invariant way. So that's one interesting thing. Now you might even think that that's an accident. It's an accident that exactly, literally the same structure shows up in these two different problems. Were it not for the fact that Juan and Davide and Pedro Vieira and friends and Amit Sever discovered that exactly the same Hitchin system equations that show up in the wall crossing phenomenon describe the strong coupling amplitudes. So it's not only is it not a coincidence, in some limit, one structure turns into the other structure. So that's one place where these objects show up. Another place where not literally the same, yes. The amplitudes in the strong coupled limit are characterized by these Y system equations and these Hitchin systems and so on and so forth, which very surprisingly 3 years ago were related to the same equations that showed up in wall crossing, right? Now we see that the structure I'll be talking about tomorrow has to do with the amplitudes for n equals 4, the Yangian, leading singularities, cluster algebras, all this kind of stuff, okay? Literally the same structure. Not analogous, literally the same structure, doing two very different things, asking two very different questions of literally the same structure. And I'm saying it can't be a complete coincidence. If all we knew was wall crossing and amplitudes in the way that I'll describe them, it would seem like a coincidence. But we also know that the strong coupling amplitudes have to do with exactly the same thing. That's some indication that this is not, whatever it is, goes beyond just planar n equals 4. It knows about other things as well. It knows about S-duality in particular. Right. Well, the sense in which they're identical is not the sense in which they're identical is not obvious. But let me say one more thing. So some of what I will not have a chance to talk about, very likely, is that on the amplitude side, we see that this goes well beyond the planar limit. Planarity is, there's some structure there well beyond the planar limit. There's no obvious integrability. There's no obvious Yangian. There is something locally integrable on the world sheet, if you like, and that has some remnant, but it goes well beyond the planar limit. We haven't solved the theory yet beyond the planar limit, but we're starting to solve it. I mean, there are whole infinite chunks of it that are starting to come under our control. That's another thing. The final thing is that not literally the same mathematical structure, but a very analogous one shows up in this Kahn-Kreimer et al. Story that understands the origin of the renormalization group and sees this sort of Hopf algebra structure that underlies the old-fashioned BPHZ way of thinking about the renormalization group in quantum field theory. that was a set of ideas that Kahn and Kreimer and friends have been talking about for 15 years that I was always totally allergic to, because I thought it's a totally stupid way of doing in some highfalutin language something that we understand beautifully locally, but there is another point of view, which is that there's some machinery that gets asymptotic questions, and very similar machinery also controls and understands the origin of the renormalization group. So those are the reasons I'm optimistic. But of course, until it's really done, we don't know. So David's absolutely right to bring it up, and it could be that it's all a mirage of integrability, and the second you go one step beyond it, none of it works. I really very, very highly doubt it, but I think it could well be.
What happens when you go along the Higgs?
Yeah, the Higgs branch work is great. People have started computing the amplitudes on the Coulomb branch. It's great. Yeah. Yes, of course. No, that's why I said masses are not a problem. Yeah, masses are not the problem. The renormalization group is the real problem. It's not masses. It's something that's deeply has to do with locality. And understanding that's why I say a real crisp or some picture for the renormalization group from these on-shell methods would really be something, because it would really be decoding the hologram, if you like. It would really be telling you where local physics comes from strictly on-shell point of view. And I should say that if you even ask it one loop, the very simple question, when we compute amplitudes, not for n equals 4, but for QCD, for n equals 1, for other theories, when we compute them using these fancy on-shell methods, okay, you can get the beta function. No problem. You can get the 11/3 and stuff, no ghosts, no nothing, everything with beautiful on-shell formulas. Okay, it's been done. I think Lance Dixon had some nice notes on it around 7 years ago. There have been a number of papers on it recently. But something remarkable happens. You find that you compute the beta function, okay? So you get it. You can get the 11/3 and everything. But it is not at all obvious when you compute things with this on-shell method, that the logarithmically divergent, UV logarithmically divergent part of the answer is actually proportional to the tree amplitude. I mean, that most basic thing, which is obvious from the local perspective, that it's just the renormalization of the coupling, right? That most basic thing is not obvious when you compute things with these on-shell methods. Indeed, for it to be true, some incredible seeming identity between tree amplitudes needs to be true. Because you compute all these things, after all, just by sewing tree amplitudes together, okay? So you find that there's really some identity that you have to prove that encodes the fact that the divergences are local, okay? And there's some remarkable identity about tree amplitudes that's got to be true. Now I can go about trying to prove this identity or understand where it comes from. They're really miraculous seeming identities. But something is controlling those identities, and I think understanding where those come from would begin to get at the real heart of the question David was asking. I think the really deep question is not masses, but scale dependence and the renormalization group. And actually then, of course, that's the most basic part. After that, you want to see that the two-loop leading logs are the same as the one-loop leading logs and so on. So that there's a whole story to try to understand. But that part of it, that gadget that controls how the leading logs and subleading logs organize themselves recursively, is what this Hopf algebra structure that Kahn and Kreimer talk about is all about. And exactly the same kind of Hopf algebra structures show up in the sorts of objects that we're talking about. So that, yeah.
So, as long as you don't have time for anything else. The way you put it is locality looks like a miracle. You really need to understand how locality emerges.
Right.
But does that also mean that there are natural, beautiful structures here?
Absolutely. Which aren't local, yeah, right.
Which aren't local.
Yeah. Yeah.
I mean, with some physical interpretation.
Not local, yeah. I mean, like take an individual BCFW term. Okay, it's a beautiful thing. It isn't local. It's perfectly Yangian invariant. It's right. But you mean something more, right. Yeah, right. That's right.
I mean, some structure like.
Well, but yeah. So yeah, no, yeah. So this is of course the finding a natural deformation is really the ultimate goal, right? I mean, if I push the analogy of the philosophy at the beginning part of the talk, You ultimately want to discover quantum mechanics. Only step one is reformulation to find the least action principle. Then you have to be imaginative enough to figure out how to invent the path integral from there. In the analog, we're not even at step one yet. We haven't even found, I mean, there's lots of progress, but we haven't found a crisp thing that you can explain, you know, in three sentences, the idea for what the whole reformulation is, right? But if it exists, the hope is that it suggests, once you think about it properly, it suggests a natural deformation. And it's not picking out random crappy pieces, but it's something a little more interesting. And I mean, so doing it for locality is interesting, and doing it for unitarity, both. Something I probably won't have time to talk about in these lectures is a whole sort of dual set of structures that, which, dual to the ones that I'm talking about here, that I'll be talking about here, which seem to think of amplitudes as some generalized sorts of volumes of something, of some sort of polytopes that live in some space. And so think of it roughly. There's some polytope. And to compute the amplitude, you've got to triangulate this polytope in some way. And there are different ways of triangulating it. And different triangulations make different physical properties manifest. Some triangulations make locality manifest. Some triangulations make unitarity manifest. There's no one triangulation that makes both of them manifest. So you see this tension between locality and unitarity, which we normally, in quantum field theory, resolve by introducing huge amounts of gauge redundancy. And this picture is reflected in a totally different way. They're literally complementary to each other. You have some object, and you triangulate in two ways, and one makes locality manifest, one makes unitarity manifest. So if something like that is true, and we figure out what it really means and how it works in general, then perhaps that's a natural place to deform what the object is. And then each triangulation, which before gave you something exactly local and exactly unitary, might suggest some sensible way of talking about its deformation on both sides. Okay, so tomorrow we will finish talking about some of the very basics about the transition to going from these space-time variables to momentum variables, or the lambda tilde variables. This involves a half Fourier transform. We'll actually discover this half Fourier transform in a very dumb pedestrian way by just writing down a solution to the massless wave equation, the way we should do in beginning graduate courses, but we don't for some reason. Okay? So if you just write down solution to the wave equation in the most sensible way possible, you immediately discover this thing called the Penrose transform and the half Fourier transform and all the rest of it. And we'll also talk about the twistor variables that are associated with the dual space-time, the so-called momentum twistor variables. And then we'll start talking about the Grassmannian, just for a little bit of orientation. And then I'll put a full stop, and we'll start from the other end. And I'll start by talking about permutations. The same way. I mean, there's nothing. This is all very, very intrinsically Lorentzian. So, but you can still rotate the Euclidean in the usual way.
Do you know, by the way, about